Every airplane you have ever flown on weighs somewhere around 100,000 pounds. Some of the big ones, 200, 300,000 pounds. Metal, fuel, luggage, people. 300 people sitting in rows, reading magazines, eating peanuts, complaining about the person in front of them, reclining their seat. And the whole thing, all of it, is just hanging there in the air, moving through nothing but air, which, as you well know, you can wave your hand right through without much trouble. You are sitting there at 35,000 feet, eating a little bag of pretzels, and between you and the ground there is nothing. 6 miles of nothing. The thing holding you up is not a cable. It is not a balloon. It is not magic. It is a physical interaction between a shaped piece of metal and the surrounding air. And that interaction has to generate a force equal to the entire weight of the airplane continuously for hours. One moment of failure, and you are a rock. So it seems like the kind of thing you ought to understand. And if you ask somebody how it works, if you corner a physics teacher, a pilot, your uncle who once read a book about airplanes, 9 times out of 10 you will get the same answer. They will say, well, you see, the wing is shaped so that the top is curved and the bottom is flat. The air that goes over the top has to travel a longer distance than the air that goes underneath. But both streams of air have to arrive at the back of the wing at the same time. So the air on top has to move faster to cover that longer distance. And Bernoulli's principle tells us that faster moving air has lower pressure. So there is lower pressure on top, higher pressure on the bottom, and that pressure difference pushes the wing up. Lift. That explanation is everywhere. It is in high school textbooks. It is in encyclopedias. Pilot training manuals have used it for generations. Museums put it on the little plaques next to model airplanes. I have heard university professors say it with great confidence and a pointer and a diagram. And every single part of that explanation, taken as a complete package, is wrong. Not a little wrong, fundamentally, structurally, irredeemably wrong. And I can prove it. But before I tear it apart, let me be fair. Because the people who teach this story are not stupid. There is something deeply seductive about that explanation. It has a beautiful logic to it. Air splits at the leading edge. One path is longer than the other. The longer path means faster speed. Faster speed means lower pressure. Lower pressure means lift. Each step seems to follow inevitably from the one before. It is a chain of reasoning that feels almost airtight. And that is exactly why it has survived for so long. Beautiful wrong ideas are the hardest to kill. They resist all evidence because they satisfy the mind so completely that people stop looking for trouble. So let us take it seriously for a moment. Let us really examine this explanation with the respect it does not deserve, but with the care that the topic demands. The core claim is what aerodynamics call the equal transit time theory. Sometimes people call it the longer path theory. The idea is this: a parcel of air that gets split at the front of the wing, the leading edge, must rejoin at the back of the wing, the trailing edge, at the same instant. The molecule that went over the top meets its partner that went under the bottom, right there at the trailing edge, and they continue on their way together, like two friends who take different paths around a building and agree to meet at the far corner at exactly the same time. One takes the short way through the alley, the other takes the long way around the block, but somehow they both arrive together. Sounds reasonable, does it not? Sounds almost obvious. Why would the air not rejoin? It's split apart. It should come back together. There is a pleasing symmetry to it. But here is the first crack. Ask yourself why. Why must the air rejoin at the trailing edge? What physical law demands this? What equation predicts it? Think carefully. Is there some force pulling those two parcels of air back together? Some invisible rubber band? Some telepathic connection between the molecule on top and the molecule on the bottom? No, there is no law of physics, not one, not anywhere, that says two parcels of air that separate at the leading edge must arrive simultaneously at the trailing edge. You can look through every textbook on fluid dynamics ever published. You can search through Newton, through Euler, through Navier, through Stokes, through Bernoulli himself. You will not find such a law. It does not exist. It was never derived. It was never proven. It was assumed. Somebody somewhere thought it sounded right and wrote it down, and then everybody copied it. And this is not a minor quibble. This is not me being pedantic about the edges. This is the foundation of the entire explanation. And everything that follows, the faster speed on top, the lower pressure, the calculated value of the lift, all of it depends entirely on this one assumption. Pull out this one brick and the whole building collapses. And the brick is made of air. Now somebody might say, all right, fine, maybe there is no strict law, but maybe it is approximately true. Maybe, in practice, even if there is no law commanding it, the air just happens to rejoin roughly at the trailing edge. Some things in nature are like that. Things settle into patterns without being forced into them. So people have tested this. You can do it yourself if you have a wind tunnel and some smoke, or you can look at computational simulations that solve the actual equations of fluid flow. You release two streams of air side by side at the leading edge, one going over the top, one going under the bottom, and you track them to see where they are when they reach the trailing edge. What you find is striking. The air over the top does not just barely beat the air underneath. It arrives dramatically sooner. The parcel that went over the top is already long gone, well past the trailing edge by the time its partner from the bottom surface finally shows up. The velocity over the top of a real wing at a real angle of attack is far, far higher than the equal transit time theory predicts. The two parcels do not rejoin. They are not even close. They are not in the same zip code. So the very first premise, equal transit time, is not just wrong. It is spectacularly wrong. It is wrong by a large, measurable, embarrassing margin. But it gets worse. The explanation relies on the wing having a longer curved top surface and a shorter flat bottom. That is how you get the path length difference that supposedly drives everything. So consider a symmetric airfoil. A wing whose cross-section is perfectly symmetric. Same shape on top and bottom. Same curvature. Same path length. According to the equal transit time theory, this wing should produce exactly zero lift. No path length difference, no speed difference, no pressure difference, no lift. Except symmetric airfoils fly beautifully. They generate plenty of lift. You tilt them a little bit, give them what we call an angle of attack, and up they go. You can watch them in a wind tunnel. You can fly an airplane with symmetric wings. The theory says it is impossible. The wing says otherwise. And it gets even worse still. Airplanes can fly upside down. Aerobatic pilots do it all the time. They roll the airplane inverted and just keep going. When the plane is upside down, the curved surface is now pointing toward the ground and the flatter surface is on top. According to the equal transit time theory, the lift should now push the airplane downward into the ground faster. But of course the plane flies perfectly well upside down. The pilot adjusts the angle and everything works. The theory predicts the opposite of what happens. That is about as wrong as a theory can get. Or think about a paper airplane. A flat sheet of paper folded into a dart. There is no curve on top. There is no curve on bottom. The top and the bottom are the same surface. Same shape, same length, same everything. Where is your path length difference? There is none. Yet paper airplanes fly. Every child knows this. Every child who has ever folded a piece of paper and thrown it across a classroom has experimental evidence contradicting the standard textbook explanation, and most of them do not even realize it. So the equal transit time theory fails in at least 4 completely independent ways. The premise of equal transit has no physical basis. The predicted velocity is far too low. Symmetric airfoils contradict it. Inverted flight contradicts it. That is not a theory with some rough edges that need sanding. That is a theory that has been demolished. And while we are demolishing things, let me address another famous claim that you hear at dinner parties. According to the laws of physics, a bumblebee should not be able to fly. People love repeating this because it sounds delightfully mysterious. The little bumblebee defying the arrogant physicists. Nature outsmarting the equations. The claim has a real origin, but it has been twisted beyond recognition. Sometime in the 1930s, somebody applied the standard equations for fixed-wing aircraft lift to a bumblebee's wings and got a number that said it should not fly, which is perfectly correct. A bumblebee cannot fly using fixed wings. A bumblebee is not a tiny airplane. Its wings do not hold still. They flap, they twist, they rotate, they create complex vortices on each stroke. The aerodynamics of insect flight is utterly different from the aerodynamics of an airplane. When you apply the correct equations, the ones designed for flapping, rotating, unsteady flow, the bumblebee flies just fine. There is no mystery. There was never a mystery. There was only somebody using the wrong formula for the situation. It is like calculating the area of a triangle using the formula for a circle, and then announcing that triangles are geometrically impossible. The formula is not wrong. You are using the wrong formula. Both myths, the airplane one and the bumblebee one, spring from the same era, taking a simplified model too seriously and then blaming physics when reality disagrees with the simplification. Physics is not wrong. Your model was too simple. Now I want to be careful about one thing, because people sometimes make the opposite mistake. They hear that the equal transit time explanation is wrong, and they conclude that Bernoulli's equation must be wrong. That is not the case. Bernoulli's equation is a perfectly valid piece of physics. It relates pressure and velocity in a flowing fluid. And if you know the velocity distribution around a wing, Bernoulli will correctly give you the pressure, and from the pressure you can correctly compute the lift. The equation is fine. The problem is not Bernoulli. The problem is the equal transit time assumption, which people use to guess the velocity, and the guess is wrong. Way wrong. Bernoulli is innocent. Equal transit time is the criminal. They should not be charged together. All right, so if the standard explanation is wrong, what is actually going on? How does a wing really produce lift? Let us build it from scratch. Forget wings for a moment. Forget Bernoulli. Forget curves and paths and everything you were taught. Start from the most basic physical principle I can think of. Newton's third law: you push something, it pushes you back. Action and reaction, equal and opposite. You have done this experiment yourself, I guarantee it. You are riding in a car on the highway. You stick your hand out the window. You flatten your hand so it is parallel to the road. Not much happens. A little bit of drag maybe, the air pushing your hand backward. But the air flows over your hand and under your hand pretty smoothly, and there is no force pushing you up or down. But now tilt the front edge of your hand up, just a few degrees. Immediately you feel a powerful force shoving your hand upward. It is startling how strong it is. You have to fight it with your muscles to keep your hand steady. What happened? Your hand, tilted at an angle to the oncoming air, is deflecting that air downward. The leading edge catches the airstream and redirects it so it leaves your hand moving more downward than it was before. Newton says if you push air down, the air pushes you up. That is lift. At the most fundamental level, that is all lift is. A wing deflects air downward and the reaction force pushes the wing upward. But let me be more specific, because deflecting air downward might sound vague. What I mean is this. Before the wing arrives, the air ahead of it is basically still or moving horizontally with the general wind. After the wing passes, the air behind it is moving distinctly downward. This is called downwash. You can measure it. You can see it in smoke trails behind a wing in a wind tunnel. Behind every airplane in flight there is a sheet of air moving downward, and the total downward momentum of that air per unit time is exactly equal to the weight of the airplane. It has to be. Conservation of momentum demands it. The airplane pushes air down with a force equal to its weight, and the air pushes the airplane up with an equal and opposite force. If you watch a large airplane fly low over a lake, you can sometimes see the downwash disturbing the surface of the water. This is why the angle of attack is so crucial. The angle of attack is the angle between the wing's chord line, roughly from leading edge to trailing edge, and the direction of the oncoming air. Increase the angle, deflect more air downward, get more lift. Decrease it, deflect less, get less lift. It works for flat plates, for curved wings, for symmetric wings, for your hand out the window. It even works for inverted flight, because the pilot adjusts the angle of attack so the wing still deflects air downward even though the plane is upside down. The shape of the wing helps, certainly. A well-designed curved airfoil is much more efficient than a flat plate. It generates more lift for less drag at a given angle. But the fundamental mechanism is always the same: deflect air downward, get pushed up. There is also a maximum. You cannot keep tilting the wing steeper and steeper and getting more and more lift forever. At some critical angle, typically around 15 to 20 degrees for most airfoils, The smooth flow over the top of the wing can no longer follow the surface. It detaches, it separates. The smooth attached flow is replaced by a turbulent, chaotic mess. The lift drops precipitously, and the drag shoots up. This is called a stall. It is what happens when a pilot pulls back too hard on the controls. The wing exceeds its critical angle, the flow separates, and instead of a nice smooth pressure distribution, you get chaos. This is dangerous, obviously, and pilots spend a lot of time learning to recognize and recover from stalls. This Newtonian picture is correct and important, but it is incomplete in a way that matters. And I should mention something interesting here. When the Wright brothers were working out how to build their airplane in the early 1900s, they did not have Prandtl's boundary layer theory. They did not have the Kutta-Joukowsky theorem. They did not have any correct theoretical explanation of lift. What they had was a wind tunnel, a homemade one built in the back of their bicycle shop. And they had patience. They tested over 200 different wing shapes, measuring the lift and drag of each one. They built tables of data. They worked empirically, by experiment, by trial and error. They got it right, not because they understood the theory, but because they measured carefully and let the data guide them. The theory came later. The airplane came first, which is a humbling reminder that understanding why something works is not always a prerequisite for making it work. But it helps. It helps enormously once you have it to make things work better. If you only think about Newton's third law, you might imagine that only the bottom of the wing does the work, like a paddle slapping the air downward. And that is not the whole story. Not even close. Measurements show that about 2/3 of the lift on a typical wing comes from the top surface. Not the bottom, the top. The top, there is a strong region of low pressure above the wing that sucks the wing upward, and this contributes more to the total lift than the high pressure region pushing from below. So we need to understand what is happening above the wing and why the pressure there is so low. This is where things get genuinely interesting. And a little surprising, air is sticky. I know that sounds absurd. You walk through air every day and it does not feel sticky. But at the molecular level, air molecules interact with surfaces in a very specific way. Right at the surface of the wing, the air velocity is 0. The air literally does not move relative to the wing at the point of contact. This is not an approximation, not a simplification. It is one of the most fundamental and well-verified facts in fluid dynamics. It is called the no-slip condition. Think of it this way. Imagine you have a deck of cards. The bottom card is glued to the table. You push the top card forward. Each card drags the one below it a little bit. You get a gradient, a smooth transition from moving at the top to stationary at the bottom. That is what happens to air near a wing surface. Right at the surface, the air is still, a fraction of a millimeter away. It is moving a bit. A few millimeters away, it is moving faster. And eventually, maybe an inch from the surface at cruising speed, the air reaches the full velocity of the oncoming flow. This thin region of velocity transition is called the boundary layer. Think of it this way. Imagine a river flowing past a bank. A bank. And it's right at the bank. The water is not moving. It is held in place by the mud and the rocks. But a foot out from the bank, the water is drifting slowly. 2 feet out, it is moving faster. In the middle of the river, it is flowing at full speed. There is a gradient, a smooth transition from 0 velocity at the bank to full velocity in the main stream. The boundary layer in air over a wing is the same idea, except the layer is incredibly thin and the fluid is air instead of water. The boundary layer on an airplane wing at cruising speed is astonishingly thin, less than an inch in most places, sometimes just a few millimeters near the leading edge. A sliver, a whisper of sluggish air clinging to the aluminum, and you might think, well, something that thin cannot possibly matter much. It is to the wing what a coat of paint is to a building. Negligible. You would be spectacularly wrong. That thin layer changes everything about the flow. It is one of the great surprises of 20th century physics that something so small could have such enormous consequences. And this brings us to one of the great intellectual breakthroughs in the history of physics, courtesy of a German physicist named Ludwig Prandtl. In 1904, at the Third International Congress of Mathematicians in Heidelberg, a young German physicist named Ludwig Prandtl stood up and gave a talk, just 8 pages of notes. Nobody in the audience had any idea they were witnessing the birth of modern aerodynamics. Prandtl's insight was breathtaking in its elegance. For over a century, people had been stuck. On one side, they had beautiful inviscid flow theory that was mathematically tractable but gave absurd answers like zero drag. On the other side, they had the full viscous equations of Navier and Stokes, which were correct but impossible to solve for any practical problem. Prandtl broke the deadlock by dividing the world in two. Far from the wing, the air behaves almost as if it has no viscosity at all. The inviscid equations work beautifully there. But very close to the surface, in that thin boundary layer, viscosity dominates, and you must account for it. The equations in the boundary layer are simpler than the full Navier-Stokes equations because the layer is so thin. By solving the boundary layer equations near the surface and the inviscid equations everywhere else, and stitching the two solutions together, you can get answers that match reality. 8 pages, and it opened up the entire field. People rightly call Prandtl the father of modern aerodynamics. Before Prandtl, the theorists and the experimentalists were living in different worlds. The theorists working with inviscid equations could not predict drag. The experimentalists, measuring actual forces on wings and bodies, had numbers the theorists could not explain. Prandtl built the bridge between them. He showed how a vanishingly thin layer of viscous fluid could produce effects that the bulk inviscid theory completely missed. What the boundary layer does, in practical terms, is this. Because of viscosity, the flow over the wing has to obey certain constraints. It has to leave the trailing edge smoothly. It cannot whip around the sharp trailing edge from the bottom to the top. The viscous forces in the boundary layer prevent that sharp turn. Instead, the flow separates cleanly at the trailing edge. This smooth departure is called the Kutter condition, named after the German mathematician Wilhelm Kutter. When the wing first starts moving, when the airplane begins its takeoff roll, the flow initially tries to wrap around that sharp trailing edge. For a brief moment it tries, but it cannot sustain this. The viscous forces in the boundary layer cause the flow to separate, and a small spinning vortex gets shed off the trailing edge. This is called the starting vortex. You can see it in wind tunnel experiments, a little swirl of air that gets left behind as the wing begins to move. Here is where it gets elegant. There is a theorem in fluid dynamics called Kelvin's circulation theorem. It says that in an inviscid fluid, the total circulation, the total amount of rotation in a closed region of fluid cannot change over time. When the starting vortex is shed with a certain amount of spin in one direction, an equal and opposite amount of spin must develop elsewhere. And where does it develop? Around the wing itself. This is called the bound circulation. Circulation is a strange concept if you have not encountered it before. It does not mean the air is spinning around the wing like water in a bathtub drain. There is no visible swirl. What it means is that if you trace a mathematical loop around the wing and add up the velocity of the air along that loop, component by component, the total is not zero. There is a net push in one direction around the loop. It is a property of the flow pattern, not a visible rotation. And this circulation, this mathematical property, is directly responsible for lift. There is a beautiful theorem, the Kutter-Joukowski theorem, developed independently by Wilhelm Kutter and the Russian physicist Nikolai Joukowsky in the early 1900s. The theorem says that the lift per unit span of the wing is exactly equal to the fluid density times the free stream velocity times the circulation. 3 quantities multiplied together, and you get the lift. That is the whole formula. Density times velocity times circulation. It is one of the most elegant results in all of fluid dynamics. If you know the circulation, you know the lift. If you know the lift, you know the circulation. They are locked together by this simple, exact relationship. What makes this remarkable is how universal it is. The theorem does not care about the specific shape of the airfoil. It does not care whether the wing is thick or thin, curved or symmetric. As long as you know the circulation, you know the lift, all the complexity of the flow, all the details of the pressure distribution and the velocity field boil down to a single number, the circulation. So the chain of cause and effect goes like this. The wing moves through the air. Viscosity in the thin boundary layer enforces the Kutta condition at the trailing edge. A starting vortex is shed. Kelvin's theorem requires an equal and opposite bound circulation to develop around the wing. That circulation produces a pressure distribution, low on top, high on the bottom, which we can calculate using Bernoulli's equation applied to the actual velocities, not the fake velocities from the equal transit time theory, and this pressure distribution integrates to give us lift. And every step is based on real physics. Every step is measurable and verifiable. Every step follows from the equations of fluid dynamics. Both surfaces contribute. The bottom deflects air downward by direct interaction. The top, because the flow follows the curved surface and then curves downward toward the trailing edge, also deflects air downward. The net effect is a substantial downwash behind the wing, a region where the air is moving more downward than it was before it encountered the wing. By Newton's third law, the wing is pushed up. And critically, none of this requires the equal transit time assumption. None of it requires the air to rejoin. None of it requires one path to be longer than the other. It all follows from the real physics of viscous flow, boundary layers, and the Kutta condition. Now let me take you somewhere strange, somewhere that will make you uncomfortable. Back to the 18th century, to one of the most embarrassing results in the history of physics. In 1752, a French mathematician named Jean-Laurent d'Alembert did a calculation. D'Alembert was brilliant. He was one of the editors of the great encyclopedia, the monumental reference work of the French Enlightenment, and he was a superb mathematician. He asked what seemed like a simple question: what force does a fluid exert on a body moving through it at constant speed? He used the best theory available, incompressible, inviscid potential flow, a perfectly smooth, perfectly frictionless fluid. He set up the equations. He did the integral around the body. He checked his work, and he got an answer that horrified him. Zero. The net force was zero, not just the lift, the drag too. A body moving at constant speed through a frictionless fluid experiences no resistance whatsoever. No drag, no lift, nothing. The fluid parts perfectly ahead of the body and closes perfectly behind it, and the pressure pushes equally in all directions, and the whole thing adds up to precisely nothing. D'Alembert knew this was absurd. Ships obviously experience resistance in water. Arrows slow down in flight. A person walking through a strong wind feels a force. The mathematics was impeccable, but the conclusion was ridiculous. He published the result and said with admirable honesty that he would leave the resolution of this paradox to future geometers, and it took 150 years to find the answer. And 150 years of the smartest people in Europe being stumped by the question of why a frictionless fluid gives the wrong answer. You might think the answer is obvious. Well, real fluids are not frictionless. True. But here is the puzzle that kept people up at night. Real fluids like air and water have very little viscosity. Air is barely viscous at all. It feels like it should be very close to the inviscid ideal. So why does the inviscid theory not give an approximately correct answer? Why does it give an exactly wrong answer? Zero is not approximately correct. It is maximally wrong. How can the tiniest bit of friction produce a gigantic change in the answer? This is the puzzle that Prandtl solved with his boundary layer. What? The answer is that no matter how small a viscosity, it creates a boundary layer where its effects are concentrated. And that boundary layer, no matter how thin, changes the fundamental character of the flow. It introduces asymmetry. It allows separation. It permits drag. The effect is not proportional to the amount of viscosity. It is a qualitative change, not a quantitative one. A tiny amount of friction does not produce a tiny amount of drag. It produces a completely different kind of flow. Mathematicians have a name for this kind of behavior. They call it a singular perturbation. The inviscid limit is not the smooth, well-behaved limit you might expect. It is wild, discontinuous. The solution at zero viscosity is fundamentally different from the solution at any non-zero viscosity, no matter how small. It is as if you are walking along a smooth path, and suddenly there is a cliff. You cannot tiptoe up to frictionless flow. You fall off the edge. This is the part that I find genuinely wonderful, the part that gives me the chills when I think about it. The most idealized, mathematically pristine version of fluid flow predicts that flight is impossible. In a perfect frictionless world, there is no lift and no drag. Nothing interesting happens. A wing does nothing. An aeroplane sits on the runway and never moves. And what rescues flight from this mathematical death sentence is friction. The very thing you would think works against an airplane, the thing that creates drag and burns fuel and slows you down, is the same physical phenomenon that makes lift possible in the first place. Without viscosity, without that microscopically thin boundary layer of sluggish air, no starting vortex forms. No circulation develops, no Kutta condition is established, and there is no lift. Friction is not just the enemy of flight, it is the secret ingredient. The thing that tries to slow you down is the same thing that holds you up. Nature has a sense of irony that would make a playwright jealous. So now let me come back to the title of this talk. The airplanes should not be able to fly, and nobody really knows why. Is that true? The first part has a kernel of truth, but only in a very narrow technical sense. In D'Alembert's perfectly inviscid mathematical world, flight is indeed impossible. So if by should not you mean according to an oversimplified model that ignores a crucial physical effect, then sure, but that is like saying a car should not be able to drive because you left friction out of your model of tires. The real equations of fluid flow, the Navier-Stokes equations, which include viscosity, predict lift with no trouble at all. There is no paradox in the real physics. There is only a paradox in the simplified version. The second part, nobody really knows why, is more interesting and more wrong, but it has a subtle grain of truth that is worth examining. We know very well how lift works. We can predict it. We can calculate it multiple ways. We design billion-dollar aircraft using these calculations, and they work. Every commercial airplane ever built was designed using equations and computer simulations that correctly predict the lift. If nobody knew why planes fly, we would have stopped building them a long time ago. But the equations we use, the Navier-Stokes equations, present a deep mathematical mystery that is worth understanding. These equations were first written down by Claude Louis Navier in 1822 and refined by George Gabriel Stokes a couple of decades later. They describe how the velocity and pressure of a viscous fluid evolve in time and space. They account for everything: viscosity, inertia, pressure gradients, compressibility, if you include it, even the chaotic behavior we call turbulence. As far as we know, they are the correct and complete description of how ordinary fluids behave. And for most practical cases, we cannot solve them exactly. The difficulty is that the equations are nonlinear. The velocity of the fluid at one point depends on the velocity at neighboring points, which in turn depend on the velocities at their neighbors, in a chain of mutual influence that makes the mathematics ferociously hard. Linear equations can be broken into simple pieces and solved one piece at a time. Nonlinear equations resist this. Their pieces interact with each other, and new behavior emerges that you could not have predicted from any single piece alone. Turbulence, that beautiful, chaotic, swirling motion you see in a stream or in the smoke from a chimney, is a fundamentally nonlinear phenomenon. So we solve the Navier-Stokes equations approximately on computers by dividing the space into millions or sometimes billions of tiny boxes and stepping forward in tiny increments of time, computing the velocity and pressure in each box based on values in its neighbors. This is called computational fluid dynamics. It is one of the great triumphs of modern engineering. The answers match experiments with remarkable precision. Every modern airplane wing, every turbine blade, every car body, every bridge that must resist wind loads has been designed using these numerical solutions. They are reliable, they work, but nobody has exact analytical solutions for most real situations. And more troubling, nobody can prove that solutions to the three-dimensional Navier-Stokes equations always exist and remain smooth and well-behaved. It is conceivable that the solutions develop singularities, points where the velocity becomes infinite, blow-ups in the mathematical sense. Nobody has ever observed this in a simulation or an experiment. But nobody has proved it cannot happen. This question is one of the 7 Millennium Prize problems posed by the Clay Mathematics Institute in the year 2000. There is a $1 million prize for whoever can resolve it. As I stand here, that prize is unclaimed. It is considered one of the hardest open problems in all of mathematics. So there is a genuine sense in which our mathematical understanding of fluids has a gap, not a gap in our ability to predict or calculate. We can do that just fine, but a gap in our ability to prove with full mathematical rigor that the equations themselves always behave. Calling this evidence that nobody knows why planes fly is a bit like saying nobody understands addition, because Gödel proved that the foundations of arithmetic have inherent limitations. Or like saying nobody understands the sun because certain problems in plasma physics remain open. We understand flight, we understand it thoroughly from multiple perspectives, using multiple theoretical frameworks that all agree with each other and with experiment. The deep mathematical questions about the Navier-Stokes equations are fascinating and important, but they do not make flight a mystery any more than Gödel's theorems make 2 + 2 a mystery. And let me say something about those multiple perspectives, because this causes confusion too. Some people explain lift using Newton's third law and downwash. Other people explain lift using pressure differences from Bernoulli's equation. Others use circulation theory and the Kutta-Joukowski theorem. And some people treat these as competing explanations, as if you have to pick a side. Newton versus Bernoulli, they say, as if it were a boxing match. This is a false conflict. These are not competing explanations. There are different ways of describing the same physical reality. It is like describing a symphony. One person describes the melody, another describes the harmony, a third describes the rhythm. Are they disagreeing? No, they are all describing the same piece of music from different angles. The melody description is not wrong because it omits the harmony. The harmony description is not wrong because it ignores the rhythm. Each captures a true aspect of the whole. Newton's third law tells you the force on the wing must equal the rate of change of momentum of the deflected air. That is true. Bernoulli's equation, correctly applied to the actual velocity field, gives you the pressure distribution. And integrating that pressure gives you the same force. Also true. The Kutta-Joukowski theorem, which connects circulation to lift, gives the same number again. Also true. They are 3 roads to the same destination. You can take any of them, and you arrive at the correct answer. The only problem is when somebody takes one of these correct roads and contaminates it with a false assumption, like equal transit time. That is not Bernoulli's fault. Bernoulli was a fine road. Somebody just put a wrong turn sign on it. So why does the wrong explanation persist? Why does the equal transit time theory still appear in books and classrooms after decades of correction? I think there are 2 reasons, and they are both important. The first is that the wrong explanation is easy. It tells a clean, simple story with a beginning, a middle, and an end. Curved wing, longer path, faster air, lower pressure, lift. Each step is easy to visualize. Each step seems to follow from the one before. A teacher can draw it on a chalkboard in 2 minutes. The correct explanation involves viscosity, boundary layers, the no-slip condition, circulation theory, starting vortices, the Kutta condition, and the Kutta-Joukowski theorem. That is a much harder story to tell. It requires more time, more background, and more willingness to sit with complexity. In a world where physics education is often compressed into sound bites, the wrong answer wins because it fits in the allotted time. The second reason is deeper and more troubling. Once a wrong idea gets into the textbooks, it reproduces. A teacher learns it from their textbook. They teach it to their students. Those students grow up, and some of them become teachers, and they teach the same wrong thing to the next generation. Each person in the chain genuinely believes they are correct. They are not lying. They are not being lazy. They are faithfully transmitting what they were taught. But what they were taught was wrong, and so the error propagates generation after generation, like a miscopied gene. The equal transit time theory has been in some textbooks for nearly a century now. Think about how many minds it has passed through, how many students absorbed it, nodded, wrote it on an exam, got it marked correct, and carried it with them for the rest of their lives. NASA, to their credit, has published explicit corrections on their educational website, with detailed explanations of why the equal transit time theory is wrong. And yet, if you walk into a random high school physics classroom tomorrow, there is a good chance you will hear it taught as if it were gospel. This is one of the great dangers in science education. This is one of the great dangers, not that students will be ignorant. Ignorance is fixable. You just add knowledge. The real danger is that students will be confidently wrong. A person who does not know how lift works can be taught in an afternoon. A person who thinks they already know, who has a beautiful and satisfying but incorrect picture in their head, that person is much harder to reach. You first have to demolish the wrong picture, which feels like an attack on their intelligence, and then build the correct one, which requires more effort than starting from scratch. People resist this. It is uncomfortable to learn that something you were confident about was false. It feels like being tricked. And this is not just a problem with airplanes. It happens everywhere in physics. Electrons orbiting the nucleus like little planets. Light being a wave or a particle as if it switches costumes between experiments. Gravity is a pulling force without any sense of what Einstein showed about the geometry of space-time. Heat is a fluid that flows from hot to cold. These are all simplifications that were useful at one point, but they become dangerous when people mistake them for the truth. The map is not the territory. The model is not the phenomenon. I want to leave you with one more thought because I think it is the most beautiful thing about this whole business. If you have ever watched a wind tunnel test or even a good simulation, you have seen something extraordinary. The moment the air starts flowing over a wing, there is a brief chaotic moment at the trailing edge. The flow does not know what to do yet. It tries to wrap around the sharp edge. It fights with itself. And then, within a fraction of a second, the starting vortex peels off and floats away downstream. The circulation establishes itself around the wing. The flow snaps into its steady pattern, and lift appears. It is like watching a key turn in a lock. Everything clicks into place. And from that moment forward, the wing is flying. The air above is racing. The pressure is dropping. The downwash is forming, and hundreds of thousands of pounds are being supported by nothing you can see or touch. This happens every time an airplane takes off. Every single time. On every runway in the world. And it happens because of physics that was not understood until the 20th century, that relies on a paradox from the 18th century, that depends on a microscopic layer of sticky air that nobody can see. D'Alembert showed us what a frictionless universe would look like. No drag, no lift, no interesting fluid behavior at all. Just air sliding past objects with mathematical perfection and absolute sterility. Nothing happens. It is the most boring universe imaginable. But the real universe has friction. It has viscosity. It has boundary layers and turbulence and starting vortices and all these complicated, messy, difficult to calculate effects. And those messy effects, those deviations from the clean mathematical ideal, are precisely what make flight possible. What make weather possible, what make ocean currents sweep across thousands of miles, what make the smoke from a candle curl upward in those gorgeous, intricate spirals that have fascinated people since the beginning of time. The deviations from perfection are where the interesting physics lives. The idealized model is useful, sure. It is a starting point. But the places where reality refuses to be simple, the places where the real behavior diverges from the idealized prediction, those are the places where you find out what nature is actually doing, as opposed to what you assumed it was doing. 100,000 pounds of metal, fuel, and human beings hanging in the air at 35,000 feet, held up by friction, not in spite of the messiness of the real world, but because of it. Flight is not a triumph of simplicity, it is a triumph of complexity. It works because the universe is richer and stranger and more interesting than any simple model can capture. If that does not make you want to look more carefully at the world around you, at the steam rising from your coffee, at the ripples in a puddle, at the flutter of a flag in the wind, then I do not know what will. So next time you are on an airplane, looking out the window, watching that wing slice through the clouds at 500 miles per hour, remember this, that wing is not flying, because the air on top takes a longer path. It is flying because air is sticky, because a microscopically thin layer of slow-moving air clinging to the metal surface of the wing sets off a chain of events, a vortex shed, a circulation established, a pressure distribution created that ends with 300,000 pounds being lifted into the sky, and nobody had to command the air to do any of it. The air just does what the physics tells it to do. That is not a mystery. That is something better than a mystery. That is understanding. Tell me this. What other explanation have you been taught that you have never really questioned?